In this video, we will study the notion of orthogonal circles. In geometry, the word orthogonal is used interchangeably with another word, perpendicular, which is a well-known positional relation between two lines. For instance, if we draw a line on the Euclidean plane, then another line is said to be orthogonal to this line if the angle formed by these two lines is 90 degrees, as the example that we're looking at on the screen. Now, the question is, how can we apply this notion to other types of curves? Can we make some sense out of this term for some nonlinear curves in general? To answer this question, let's look at a common practice among mathematicians and physicists. When studying the behavior of a curve near a point, a common tool to use is the tangent to the curve at this point. After introducing the tangent line, many notions of straight lines could be translated to curves in general, including the angle formed by two lines. For instance, if we're looking at two circles which are intersecting at some point, then the angle formed by these two circles at the intersecting point could be simply defined as the angle between the tangent lines of these two circles at the intersecting point. For instance, these two circles that we're looking at on the screen will be forming an angle on the point B, whose measure could be given by 96.6 degrees if we think about the circle as this one over there. And of course, these two tangent lines also forms other angles. And the other angles are going to be either the vertical angle of this guy or supplemental angles to this angle over here. After introducing the notion of angle formed by two circles, it's natural to call two circles orthogonal to each other if the angle formed by these two circles is 90 degrees, just as what we used to call two straight lines being orthogonal to each other. To summarize, let's write down the formal definition. Two circles are said to be orthogonal if the tangents of these circles at the points of intersection are perpendicular to each other. Meanwhile, since the radius drawn to the point of tangency is perpendicular to the tangent, we could write down the definition of orthogonal circles equivalently as follows. Two circles are said to be orthogonal if the radius drawn from one of the circles to a point of intersection is perpendicular at the point to the radius drawn from the other circle. To familiarize ourselves with this new notion, let's work on the following simple theorem. It says that if two orthogonal circles have 2 points of intersection, the radii are perpendicular at both points of intersection. For instance, in the figure down there, we were given two circles which are orthogonal to each other. By definition, the radii of these two circles drawn to a common intersecting point must be orthogonal, or in other words, perpendicular to each other. Say, for instance, we were told that the radii drawn to the point B for both of those two circles are orthogonal to each other. What we need to show is that the radii drawn to the other points of intersection, which is the point D down there, are also orthogonal to each other. That's what we like to show. To prove this claim, let's join point A and point C, which are the centers of those two circles respectively. By joining those 2 points, we bring in 2 triangles, ABC and ADC. If we could show that these 2 triangles are congruent to each other, then the corresponding angle ABC and ADC will have to be congruent to each other. Hence, the angle ADBC would have to be a right angle as well. To see these 2 triangles are congruent, we first observed that the line segment AB is congruent to the line segment AD because both of them are radii of the circle centered at A with radius AB. Similarly, the line segment CB is congruent to the line segment CD as radii of the circle centered at C with CB as the radius. Lastly, the line segment AC is shared by both of these 2 triangles. Hence, we could apply the side-side-side condition. By the side-side-side condition, we conclude that the triangle ABC is congruent to the triangle ADC. Consequently, the measure of the angle ABC equal the measure of the angle ADC, both of which are 90 degrees. And that's precisely what we want to show. Thank you for watching. See you next time.